So out of chapter 6 here, we're only going to be covering 6.1 and 6.6. Now out of 6.1, we've talked a good bit about this already. Why do we balance equations? What is the purpose of balancing the equations? Well, we talked about it then as being this arm of the law of conservation of matter. That if I examine all of the things that were there as reactants, so I had, in this case, 5 oxygen atom or molecules, 10 oxygen atoms in total, and I have C3H8, so I've got 3 carbon and 8 hydrogen. If I flip it over onto the other side, I can see that I have 3 CO2s, 1, 2, 3, and I have 4 waters. Well, if I put those together, that would give me 3 carbons, 8 hydrogens, and a total of 6 plus 4 for 10 oxygens. Every atom that was here as reactant has come over as product, just in another form. And so again, we've covered this idea. The coefficients tell us that ratio of one molecule to another in a balanced equation. So when I read this equation, it tells me that 1 propane reacts with 5 oxygens to make 3 carbon dioxide and 4 water molecules. The coefficients there tell us how many of each molecule are present as reactants and how many of each molecule are there as products. So I can put that into molecular terms. Every molecule of propane reacts with 5 molecules of oxygen. And when that occurs, 3 molecules of carbon dioxide are made, 4 molecules of water are made. Now, rarely do we deal with molecules individually. Molecules are small amounts of each one of those substances. It's much more common that we think about things in terms of moles. And so if you go back a couple of chapters when we talked about moles for the first time, remember a mole is Avogadro's number, 6.022 times 10 to the 23rd molecules of a given substance. Well, since moles are a standardized unit, we can use them in the same kind of way that we did molecules. Every mole of propane is going to react with 5 moles of water, or excuse me, 5 moles of oxygen to give me 3 moles of carbon dioxide and 4 moles of water. That's what those coefficients mean. And what this can eventually lead us to is an overall description of this is what it looks like. Let's say that I have a mole of propane. Well, a mole of propane would weigh about 44 grams. So if I measure out 44 grams of propane, I could look at that and say, okay, 44 grams of propane, well, 5 moles of oxygen, that's 160 grams. So to get this reaction, I would need my 44 grams of propane, my 160 grams of oxygen, my 160 grams of oxygen, and it would give me whatever 3 times 44 is for carbon dioxide, whatever 4 times 18 is for water. I could put those out and put them together like that using molar quantities overall. And so we can see that even if we're going outside of the coefficients themselves, the relationships still hold true. So our first look here, we had a 1 to 5 to 3 to 4 ratio. Well, if I double that, let's say I have 2 molecules of propane, everything else is going to double as well. My 1 becomes a 2, my 5 becomes a 10, my 3 becomes a 6, my 4 becomes an 8. If I had 100, I'd multiply everything by 100. If I had a mole, I'd multiply everything by Avogadro's number. If I had a mole of something, if I had 5 moles of one of these, then I would change that ratio accordingly. The ratio is going to be consistent because we're talking about a very strict conservation that's going on here. And so where this takes us with regard to energy is we want to make sure that we can establish that there is a relationship between how much stuff reacts and the amount of energy output that we get. We know that when chemical and physical processes occur, there is a resulting energy that is associated with that conversion as well. If I take a block of ice out of my freezer and let it sit on my kitchen counter, there is going to be a heat transfer that occurs because the heat of my kitchen is going to go into the ice to, first of all, warm it up to room temperature and also to melt it. There is an energy change going on there. There's an energy change that goes on when you light a fire. In the case of the Bunsen burner there, you've got methane, natural gas, reacting with the oxygen to make water vapor and carbon dioxide. And the byproduct of that combustion reaction is that there is so much energy output that we see it in the form of heat and light, the fire, the flame itself. So we know that these energy changes exist. We know that in any kind of process, whether it's physical or chemical, there are going to be exchanges of energy that go on. The question is, what are those, and are there good ways that we can describe them other than this feels hot, this feels cold, and that kind of thing? As we've seen with so many other things in this class, there is a law of conservation that is associated with this phenomenon. This is called the law of conservation of energy. We've already talked about the law of conservation of matter. We've already talked about the law of conservation of mass. Now we're talking about the law of conservation of energy. And what the law of conservation of energy says is that in any process, the total amount of energy in that entire system is conserved, is constant. So if something gains energy, that energy had to come from somewhere. Something else is losing that energy. And if something gives energy away, that energy has to go somewhere. In broad scientific terms, we use the word surroundings to describe that somewhere. The term surroundings can be thought of as the environment around a chemical or physical reaction. So if I have a fire in a beaker, we would call the beaker the reaction system. That's where the chemical reaction is taking place. But everything around that beaker would be considered the surroundings. And so we can monitor changes of temperature in the surroundings to give us an idea of what's going on in the reaction itself sometimes. So if I have a fire in a barrel, as I do right here, if I held a thermometer out near the fire, not in the fire itself, but near the fire, what I would notice is that the temperature around that fire is increasing. What that means, energy is being emitted to the surroundings from the chemical reaction that's taking place in that barrel. Now, in some cases, heat is not the only kind of output. As is shown in this illustration with the car here, the combustion of octane inside of your engine does generate heat. That's why your engine feels hot after it's been running for a while. But the heat transfer is not the only conversion of energy that exists. Your engine uses that energy from that combustion reaction to drive the mechanical parts of your car and allow your car to actually take you somewhere. So not all energy conversions are just heat. There's also another phenomenon in here called work, where we can actually get the energy from a chemical process to do something, some kind of task, exert some kind of force on the surroundings. Or in other circumstances, if we flip the process, then the surroundings actually can do some work on the system. So one of the ways that we can show energy changes of this kind is through what we call reaction coordinate diagrams. These reaction coordinate diagrams are pretty easy to follow. On the vertical axis, going up and down, we have energy. And so we can see that energy is low at the bottom and increases as we go toward the top. The reason why this is called a reaction coordinate diagram is because the x-axis here, the horizontal axis, shows the progress of the chemical reaction as it takes place. So here at the origin, we're talking about the beginning of the reaction before the reaction process takes place. And over here on the right-hand side, we have where everything is after the reaction has occurred. So in the first diagram window here, the one that's marked exothermic reactions, how would we describe the energy transfer here? Are the reactants absorbing energy, or are the reactants releasing energy as they are being converted to products? So if you're on Zoom, give me a 1 for absorbed and a 2 for released. If you're here in the classroom, just show me on your fingers. 1 for absorbed, 2 for released. All right. I've got 1 response in the chat. I've got 11 people watching on Zoom. Okay. Seeing more answers coming in. Unfortunately, all the answers on Zoom are incorrect. We had it right here in the classroom. We are seeing a release of energy in the left panel. Our reactants are at a higher energy than our products. To get from here to here, you gotta release that energy. We call that process exothermic. Now, when this kind of thing happens, let's answer the second question. What happens to the temperature of the surroundings? So, again, put it in the chat, up or down. As this energy is released, what happens to the temperature? Does it go up or does it go down? All right, I'm seeing the number of downs coming in the chat. I think we've got the concept backwards here. If the reaction is losing energy, that energy has to go somewhere. That energy is going to go to the surroundings. If I'm suddenly hitting the surroundings with a ton of energy, we're going to see the temperature of the surroundings go up as it absorbs all of that extra energy. Now, in endothermic reactions, it's exactly the opposite. In endothermic reactions, we have reactants with relatively low energy that are going to absorb energy as they become products. Now, when they absorb that energy, again, that energy had to come from somewhere. Where does it come from? It comes from the surroundings. So if the surroundings are giving energy away, we're going to see their temperature go down as a result. So we did this in lab about a week, 2 weeks ago with the mineral oil and water. Not every lab did it. Some of them did. If you heat up mineral oil and water, heat them up to the same temperature, what you will notice is that they'll both decrease in temperature over time. Why are they decreasing in temperature? Because they're hotter than their surroundings is, and so they will lose energy to the surroundings in order to drop down in temperature, to get back to where everything's even with their surroundings. So what we're looking for in these cases is something called a thermal equilibrium. So after the reaction takes place, we're going to see kind of a regression to the middle where everything tries to get back to the same uniform temperature again. Kind of like when you light a candle. While the candle is lit, the area around the candle gets hot. As soon as that candle gets extinguished, or as soon as it burns out, what happens over time? The glass jar that it's in doesn't stay hot forever. It eventually loses energy and comes back to room temperature. And that would be the case in any of these things as well. When the reaction is over, we're going to see it kind of resettle itself. But while the reaction is ongoing, we're going to see these temperature changes take place. So the terminology here is exothermic and endothermic. Exothermic reactions are the ones where we release, the chemical reaction releases heat to the surroundings. The surroundings get hot, and the chemical reaction is generating lots of heat. Common examples of these are things like combustion reactions. Combustion reactions generate lots of heat, and when they generate that lots of heat, the surroundings around them feel warmer as they absorb that excess heat. There are other reactions that are what we call endothermic. Endothermic reactions are ones that absorb heat. We see these in a number of different processes. From a chemical standpoint, endothermic reactions are considerably more rare. Where we tend to see them are certain types of reactions where we're doing things like dissolving, and the process of dissolving it actually lowers the temperature of the water because of the energy that's taking to break apart that ionic crystal. Physical processes are far more common for endothermic. Again, take that example of ice. If you take an ice cube out of the freezer and hold it in your hand, the reason your skin feels cold while you're holding that ice cube is because as the ice cube is absorbing energy to go from the solid phase to the liquid phase, it's taking energy from somewhere. Where is it taking that energy from? Your hand. And so as a result, your hand feels cold as the ice takes energy from you. And so physical processes, things like melting, things like boiling, those are far more common endothermic practices than what we see in a chemical reaction. Endothermic chemical reactions are by far less common. Any questions on endothermic and exothermic and the difference between them? Okay, so the other big topic that we want to get into and discuss here has to do with quantity of heat. So how do we quantify how much heat is involved in a chemical reaction or in a physical process? So if I have something going on, how can I quantify how much heat's being transferred? Now, this is something that gets complicated quickly because it's not necessarily that the math is difficult here. It's that there are so many ways of describing the same thing. You are probably most familiar with the heat unit of the calorie. Calories are on all of your nutrition labels. Now, the calories on your nutrition labels are actually kilocalories. And we differentiate them. Calories, as written here, you'll always see calories written with a capital C. That's not just a stylistic choice. That is by convention. Calories are the same thing as kilocalories with a lowercase c. So 1 kilocalorie is equal to 1,000 calories, or 1 nutritional calorie. That's probably the most familiar unit we have for energy. Calories, nutrition facts tell us how much energy is in our food, how much energy our body can derive from the food that we eat or from the things that we drink. Where it gets confusing is the metric unit is the joule. Now, the relationship between joules and calories is a relatively simple one. There are 4.184 joules in every small c calorie, which means if we take it up to the next level, there would be 4.184 kilojoules in every kilocalorie. So there are ways to bridge them, but like I said, where it gets real confusing is the fact that we have 4 units to describe heat transfer. We have joules, we have kilojoules, we have calories, and we have kilocalories. And while they're easy to convert between them, they're also very easy to confuse with each other. So let's do some quick calculations here. 1 serving of this particular cereal, which I have to admit I want to taste because the ingredients are whole grain wheat, evaporated cane juice, and natural flavors. That sounds like a real breakfast of champions there. But 1 serving of this particular cereal has 190 calories. Not surprising that they're almost all carbohydrate given that ingredients list. What we want to know, what is the energy content in joules? So these are just conversion problems. We've done conversion problems in the past. All that we need to do is just make sure that we're using the correct conversions in the correct ways. So what we should be able to do is if we have calories, we should be able to convert that to little c calories and convert that into joules. Because I have a conversion between big C calories and little c calories, and I have a conversion between little c calories and joules. Now it's just a dimensional analysis problem. I just need to put the right numbers in the right places. 190 big C calories. Since big C calories is in my numerator here, I want to make sure it's in my denominator in my conversion. I'm going from big C calories to little c calories. There are 1,000 little c calories in a big C calorie. And now I want to go from calories to joules. There are 4.184 joules in every calorie. My calories canceled there. $190 multiplied by 1,000 multiplied by 4.184 to 3 significant figures would be 795,000 joules. And so in this problem, we can see one of the major issues that we have with joules. A joule is not a very large amount of energy. If a single serving of cereal contains nearly 800,000 joules, that's before you even put milk on it, then we're talking about a pretty considerable amount of energy in terms of how small that particular unit is. Joules are far more useful for doing things on small scales. So I do a reaction in the lab. I'm using, instead of 54 grams of substance like I would here, I'm using 0.5 grams of substance. So in these kinds of situations, we would even favor kilojoules over joules just because of the size thing. Now, one part that is integral to this overall concept is something called specific heat. Specific heat is a value that is associated with a substance in terms of how much heat does a substance have to absorb in order to increase in its temperature. So specifically, we are talking about the amount of energy to increase the temperature of 1 gram by 1 degree Celsius. That is what we mean by specific heat. How much energy does it take to increase the temperature of a substance by 1 degree if there is 1 gram? And so specific heat values come in 2 different forms. We have the metric form, joules per gram degree Celsius. We also have the imperial form, calories per gram degree Celsius. The conversion between the two is relatively simple. The specific heat for water is 4.184 joules per gram degree Celsius. Using the calories to joules conversion, that would mean that the specific heat in the imperial system would be 1.000 calories per gram degree Celsius, because there are 4.184 joules in every calorie. So what kinds of things can specific heat tell us? Well, probably best if we look at a table of values and use them for some comparative purposes. So water has a specific heat of 4.184 joules per gram degree Celsius when it's in the liquid phase. You can see that of the substances that are on this table, none of them top that. There are some that come close, like strawberries. However, you consider that strawberries are a fruit and fruits are mostly water, kind of stands to reason. But look at your other things here. Look at your metals, for example. copper, gold, iron, lead, silver, tin. Look at their specific heat values. 0.3, 0.12, 0.129, 0.234, 0.222. What does that tell us overall about metals, again, versus water in terms of their ability to heat up? What does specific heat tell us about that? Well, the smaller the value of specific heat, the less energy is going to be required to increase its temperature. You have two objects, a frying pan and a cup of water. You put both on the stove. The frying pan gets hot in a matter of seconds. The water, you're sitting there 20 minutes later and it's still not boiling. What does that have to do with anything? Well, the specific heat of your metal pan is really low. So a couple of minutes on the stove doesn't take a whole lot of energy to increase its temperature. It gets hot really quickly. On the flip side, it also cools down really quickly as well. Let's say that you get both up to 100 degrees. You've got a pot of boiling water on this side, and you've got a frying pan on the other side. You turn the stove off, you walk away. Which one of those is getting cooler faster? It's going to be the frying pan. Why? Because the frying pan also will ditch that energy much more quickly than the water will. Because it's got to ditch less energy to get cool. Whereas the water, specific heat works both ways. To go down a degree Celsius, that gram of water's got to ditch 4 joules. Whereas that gram of copper only has to ditch 0.37 joules. So through specific heat, we can get a lot of ideas about conductivity in terms of heat conductivity, transfer. Our good conductors of heat also tend to have lower specific heat values. Our poor conductors of heat tend to have higher specific heat values. Tend to make better insulators, things that trap heat in. To answer a question like this, we need one more piece of information, and that's an equation. There's an equation that links together the concept of heat mass temperature and specific heat. The equation is this. Q, the heat transferred by the reaction, is equal to the mass of whatever it is that is being changed in temperature, multiplied by the substance's specific heat, C, multiplied by delta T. Now, the delta here indicates a change in temperature. So how much is the water going to increase or decrease in its temperature? So we have all of those data here. It was 1 gram of water, 4.184 joules per gram degree Celsius is the specific heat, and 10.0 degrees Celsius is how much we want it to change by. 1 times 4.184 times 10 would give me a Q value, 41.8. Excuse me. 41.8 joules of energy. That's how much energy it would take to increase that small amount of water by 10 degrees. And so we can do this kind of a calculation for any substance, provided we had its specific heat. Yes? Yes, that's a joules over grams degree Celsius. And so my grams end up canceling out. My degrees Celsius end up canceling out. All I have left are the joules. All right, any questions before we call it a week? Okay, so there's not much left here out of this chapter. We've actually covered the majority of it. Wednesday, we will clean it up, and then we'll move into talking about chapter 7. Remember, Monday, no Zoom session, no meeting of any kind. You just take the exam. Have a good weekend.